square foot facility. You can see here, there's a training room out back. There's a building science experience center. We have a little HVAC center with 3 different mechanical systems. We have about 12 different wall sections that we play with. It's a 2-day experience. We've just put on our website our new course offerings for the year, and just would really love you to come down and experience real hands-on how air, heat, moisture flow works, and how do you control them. So thanks for that opportunity for a little plug. In terms of what I thought we would cover, and I'll do fairly quickly, why electrify? And I'll put my own take on that. I guess most of you will have an understanding of why we're doing that, but I'll give you a sense from the residential construction sector why I feel it's compelling at this point, that for any builder to think about doing this. We'll talk about the path that is there, and each one of those path items we'll talk about the challenges and the opportunities, a little bit on the benefits. And as Keegan said, we do have time for questions. I've suggested to Keegan and Kate that if there's questions in the chat that need to be, or the Q&A that seem like they should be answered right away, they'll kind of break in on me. Otherwise, we have a good opportunity for conversation at the end of my presentation. I'll be about an hour or so. So just give that a sense. So let's start with that question of why electrify. This happens to be my cottage. We call it a cottage, so it sounds cheaper. It's a vacation home, but it was built in 2015, and it's all electric, and it's in a town where gas is on the street, and everybody was shocked that why would you possibly want to do all electric. And on my agenda were things like healthier and safer, in my case, more durable. This is an area that gets power outages regularly throughout the winter, about 6 to 8 days a year. There's power outages, and you might say, well, that doesn't match electric. Well, actually it does when you take it in totality, and I'll give you that sense. Some might say it's more comfortable. That might be a little harder to justify. In my case, it works pretty well. The sustainability was a big portion of what I was interested in. You can imagine somebody who does this kind of training. And I would say simpler. The builder wouldn't necessarily have agreed that it was simpler in terms of building, but certainly in terms of my life, our lives, it created a simpler application. Those are indeed solar shingles. I wanted to demonstrate that. In fact, in this house, we tried 26 different technologies. About 20 of them worked really well. 6 of them, I would say, maybe not. One of them is that hot water solar panel you see up to the top right there. Not that I'm against solar hot water. I just have, and maybe we want to chat about in the Q&A at the end. But I just wanted to give you a sense of each might have their own reason as to why to electrify. These would be some on my list, and what I hear from as I travel North America, hear from builders and contractors and homeowners alike as to why people are making this choice. That said, many of you would know there is this new focus on carbon dioxide emissions, or more specifically greenhouse gas emissions. Sometimes we shorten that into the carbon metric. There is this global interest in being at net zero carbon emissions by 2050. We know this tends to come and go a little bit in terms of people's interest, but this is still the overarching goal. The COP session that just finished up in South America, so reaffirming our commitment to that. And when you look at those carbon metrics, it is interesting to note that we've done a pretty good job. That is, since the 1980s or so, 1980s, there's been a 34% reduction per household in terms of energy use. So that's good news, and that's pretty much true all across the country, all sections of the country. The question is it good enough? And this is despite houses getting bigger and despite lifestyle increases, I would say, in energy use. We've still done a pretty nice job, but buildings still account for about 40% of the global emissions, and that's ever so true in the United States as well. 40% of the greenhouse gas emissions are sort of associated with the building and or operation of those buildings, the construction or the operation of those buildings. So we have a significant part to play. And yes, EV vehicles, and yes, better industry and better transportation overall, but we have a big part to play. So how do we make that happen? For those of you, many of you would already know this, but just to recap, associated with housing are two things. There on the left is the embodied carbon. That is the carbon that's released as you build the house, as you manufacture the concrete, cut down the wood, make the flooring. There's carbon released, and then there's operational carbon released as the name says, as you operate the building. So how do we rationalize those two? And we often get this question, well, if you try to reduce the operational carbon by saying adding insulation, does that not impact the embodied carbon? Well, yes, it does. But as you'll see here in a second, it's pretty straightforward to say operational carbon should indeed take front and center, that it should be the focus, if you will. So we'll talk about both. Both are important, but we'll chat about that happens. In terms of that operational carbon piece, it is a function of annual energy consumption. It's as straightforward as that. The more energy you use, the more carbon is released. Other than the fact that there is an impact on the fuel or the energy choice that you make, and the emissions in generating that energy. And that is an issue in various places across North America is, how are you generating? And in general, most climate zones, most areas, most houses still across the country, their heating, space heating and domestic hot water is primarily done with fossil fuel. That's not true of all, but that's the overriding reality. And electricity runs our appliances and cooling. So we look at the energy use for both of those, and we decide what are the emission factors associated with each of those. And if we took an example, this is a 2,300 square foot house, there's carbon dioxide emissions associated with the natural gas, 53 kilograms per meter squared, sorry. And then there's electrical use. And when you combine those two, this house is emitting 9.12 tons per year of carbon dioxide equivalent. And you go, okay, how do I make that lower? That's the operational carbon. Haven't talked about the embodied carbon at the moment. And of course, the amount of carbon that's released is entirely dependent on the electrical grid. And it is fair to say that in some places you would say, my electrical grid isn't particularly clean because it's coal or diesel or natural gas. But in other areas, if you're nuclear or hydroelectric, wind, and most importantly to me, to solar, at least in an individual house context, solar. That is, if your house is all electric and at some point you put on solar panels, then in fact you have guaranteed that you are zero emissions or lower carbon footprint, if you will. So even if in the short term that you build an all electric house and it doesn't have zero carbon emissions, it has the capability of being zero carbon emissions. And that to me is one of the compelling reasons to electrify. That is, we know that the houses you build tomorrow are going to be here for the next 200 years. I mean, if you look around you in Connecticut, in your area in the Northeast, houses last a couple hundred years. So it would be a shame to saddle that house with a system that wasn't capable of being electric, at least at some point, without huge changes to that building. So that's where we're at. And so indeed the concept here is, by all means, reduce embodied carbon as much as practical. Use the materials that are less carbon, that is low carbon concrete, cellulose insulation or reclaimed glass insulation, use more wood. Those are all really good ways of lowering embodied carbon. And then lowering the operational carbon. And you'll notice that over a 30-year span, and we tend to use 30 years in this, the industry is using 30 years as their benchmark. Notice that the accumulated operational carbon far outstrips the embodied carbon. So you absolutely would say it's okay to add more insulation. We know, for example, I've done the math in all climate zones in North America, a third pane of glass in anything past climate zone 4, like even as far south as the Carolinas, a third pane of glass pays for itself in terms of the embodied carbon that went into that third pane of glass, pays for itself in terms of carbon invested within 4 to 5 years. Insulated sheathing on the outside of a building, R10, R15, pays for itself in 5 to 6 years. So we can still make really good reductions in operational carbon without blowing the budget on the embodied carbon side. So just keep that in mind as as we go through this, and the strategies therefore reduce embodied carbon, improve the energy efficiency, and looking at the best possible return on carbon, switch to electric space, and ultimately employ solar to reduce your carbon emissions. So that's one reason, is the carbon emissions. The other reason, or another reason, is codes are progressing anyway. That is, it's really in the Northeast, you're pretty much at the 2021 code. And as codes progress, what you'll find is the heating loads naturally come down. And therefore it makes it easier to get to electrification. So we always like to show that. This is, some may have seen this before, but when you consider the energy rating indexes that are used on houses and driving that down to zero energy use, so this idea of reducing your index down to zero purchased energy, this is a pretty interesting concept, and the code is using this kind of approach and looking at ways of reducing heating loads and cooling use and domestic hot water and lights and appliances, and ultimately adding back renewables to these elements, to the houses. And when you look at the code progression, this index was started in 2004, 2006. That is, a house built to the 2006 IECC would have an index of 100. A house built to the 2015 code would have an index of 60, that kind of range. And so thinking about how do we get to that zero level, and DOE's Zero Energy Program, now renamed as the Energy Efficient Home Program, and that's a HERS roughly of 40 on that scale. So this idea that we've reduced the performance, the energy efficiency, improve the energy efficiency by as much as 60% by the time we get down to HERS 40. And the 2021 code is in the 45 to 55 range, depending on where you are. So we've done a pretty nice job. And what we're getting at here is it's about the next best thing you could do is to electrify. That is, we're getting to the point where the enclosure itself, not a lot left to do. We're at a point where adding and getting to electric and getting to solar is our way to meet the ongoing needs for improved energy consumption or reduced energy consumption, I guess, is the key we want to make. And of course, there are other drivers. There's been really nice indications of what we can get to. Things like the Energy Star program, and we know the tax credits are being sunset, as is the tax credit for the zero energy. But programs like Passive House and even Energy Star's Next Gen program that are trying to get to zero emissions is at the house level. It's pretty interesting. And the reason I mentioned this, why is this in the why electrify category, is many of you are already doing this, already demonstrating. And a lot of the technologies that have come out of these programs now make it much easier for you and I, for the mainstream, to get to electrification. These are what I would call drivers for the industry in terms of the supply base. So everybody says, oh, yes, these are now available in our market. So I find that useful. And as a little example of that zero energy ready home growth, 18,000 houses as of 2023. We're awaiting the 2024 and 2025 numbers, but it's been very compelling, right? This idea that we could get a house that could be energy independent, and that again is a compelling reason to get to electrification. And to the point I was just making, that these programs and codes have shown us a path. That is, all of the technologies I'm showing here on the screen. When I started my career, there's only, well, I would say 2 of them that were really available to us. And now we have a wide range of technologies, both on the left-hand side on the enclosures, then on the mechanicals, and ultimately on the solar. We now have the technologies that make this possible. And these are synergistic. Once you've done, or as you do the enclosure, then the mechanicals, the heat pumps, and so on get much easier to do. So all of these now become mainstream technologies that we can tie into. The one I like using this one because it's I would suggest this speaks to customers that I talk to. They ask me, why electrify? And, there's nothing wrong with natural gas. Absolutely. Natural gas is amazing. There it is on the left-hand side. It's a beautiful, pretty clean flame. It still is giving off carbon dioxide, pretty clean flame at but it burns at 3,500 degrees Fahrenheit. And it might be valid to use that to sear your steak, because that needs about 700 degrees Fahrenheit. But do we need it over on the right-hand side? Do we need that to heat hot water to 140 Fahrenheit, or houses to 72 Fahrenheit? That is, wouldn't it be better to make better use of our resources? And my mother would say, waste not, want not, because if the blue flame, if as we start to use it up, once burned, can't get it back, at least for another couple 100 million years, we're not going to have generated any new natural gas. So let's use it for what it's good at, that is melting iron ore to make steel and so on. And let's find other technologies to heat our houses. And it means in a housing context, we don't have those open flames, the emissions, and so on. So I think that's a kind of a compelling message. Is one of our good friends, Jim Moore, Beezer Holmes, likes to say, it's like cutting cheese with a chainsaw. Let's cut the cheese with a cheese knife and not use the chainsaw to do something that's more valuable. That the flame is more valuable for other things. So those would be my reasonings for electrification. I'm anxious or interested in hearing yours afterwards, or I'm interested in hearing any skepticisms or yeah buts that you might have around this particular topic. And so let's then switch to and talk about the path to electrification, see where that takes us. I'm going to use, hopefully you're okay with it, I'm going to use the Energy Star Next Gen program requirements as an example of path forward. I'm not suggesting you have to build Next Gen, but it's been a fairly thoughtful program, as frankly all of EPA's and DOE's programs are pretty thoughtful as to they're respectful, I would say, of building science. So I'm going to use it as the path forward. Again, others will be well past that in terms of PASFOS and so on. But I just want to highlight the practicalities of getting to an all electric house. I just put this up quickly to say this concept, a home for tomorrow. Understanding that EPA did a lot of focus groups on this, a lot of testing, and there is a notion by a significant number of homeowners, what is coming? I am building a house. It is my forever home. What should I be looking at in my home? And that was exactly the reasoning behind my wife and I building that all electric, in that case, net zero house, is because we imagined generations from now that our kids and our grandkids would be occupying that house and wanting to know what would be simplest and easiest for them. So this brochure spoke to me pretty nicely. Turns out in the Next Gen program, there are 5 basic elements. The first has nothing to do with electricity at all. It has to do with a highly efficient building construction. That is, first things first, fix or address the enclosure. I don't think there'll be any surprise to most of you on this call, but it's not about switching out appliances at this point. It's about, let's see if we can optimize at time of new construction or in existing houses. How could we make the building itself more energy efficient? Just use less units of, whether it's kilowatts or cubic meters of gas or liters of propane or gallons of oil, gallons of propane. Let's just talk about making the building more efficient. Second would be to switch to an electric-based heating system, like a heat pump. Third, let's think about doing that with water heating. Don't need the blue flame for the water heating either. The maybe more controversial, could we get to clean electric cooking, that is non-fossil fuel-based cooking? And lastly, and I won't talk too much about the electrical vehicle charging, but that's part of the mix as well, just allowing the house to help you on the transportation side as well. So 5 basic elements that we want to talk about. I'll just, again, go a little deeper into each one of these. First is that in terms of the Energy Star Next Gen program, they're asking you to build to the Energy Star New Home Program version 3.2. So we'll highlight exactly what that means. Or you would say, let's go further than that. Let's go to the Zero Energy Program, or better yet, let's go Passive House, because that would allow us to reduce our energy consumption overall, and less need for any amount of energy in that energy fuel or sources in that house. So keep that in mind. Again, second is going to that certified multi-speed heat pump. And in this case, certified 2-speed or variable speed. Pretty critical here, the third bullet down, is EPA's connected criteria, an interest, if you will, in making sure that we have access to the ability in the future to be able to control from a demand management side. And I'll come back to that in a little bit. From the demand management side, could I use it as part of a storage mechanism, if you will, to offset or load shift? The fourth bullet, I think, is important as well. We often worry about heat pumps and whether they're going to perform correctly. The Energy Star Next Gen program takes care of that, or at least largely, by saying we need to make sure it's installed as per the most recent standards to a grade 1 standard. So I think that's useful. Similarly, on the heat pump side, the Energy Star program, sorry, on the water heater side, heat pump program has a very specific requirement for certified heat pump water heaters at a very specific capacity. I'll go to bed to 3-bedroom, 59-gallon capacity with a very specific sound rating if the water heater is in an occupied space or occupiable space. So very specific requirements there. And then lastly, as I mentioned, the electric cooking may be a bit controversial, except many of you who've experienced would say, well, the induction range do really well. They're not a requirement of the program, but I would suggest to you, if you're going to do this, then you would say, I'm going to do induction cooking because it gives you the similar, if not better performance than gas. And as I mentioned, lastly, the electric vehicle charging capabilities, very specific requirements in Energy Star Next Gen. I'll say probably a few times, I'm not suggesting you have to do Energy Star Next Gen. It's a voluntary program. EPA is the first to say that. It just gives us a good guideline as to where we should go. And so in that first requirement, that was to optimize the enclosure, build an efficient house, and we would say use building science. Unfortunately, I get to do more of this in 2 weeks. Today, I'll just highlight a few elements of that, but it's about striving for Energy Star or DOE's efficient new home. And again, many of you are beyond that in terms of passive house levels. And when we imagine ourselves doing that, useful to know that we know where the energy is going. The energy modeling, more importantly, the energy research done in the 70s, 80s, and 90s showed us where the energy usage was. Notice on the left-hand side, a big chunk of it due to air leakage, basements, not so much in attics. Why? Because we are already insulating attics. As we move ourselves down towards the right-hand side, HERS index of 50, 40 in the range of, say, a passive house, 35 or 40, we can see that we have dramatic differences in terms of the percentages, if you will. And something to keep in mind here is notice that both the basement and the walls become a bigger and bigger piece of the puzzle, if you will, or piece of the pie. And that's because typically we do the others first, right? We changing walls and changing foundations is seen as expensive, so we don't necessarily take a stab at that. There's only 2 of these items I'm going to have time to talk about today. I'll do a little bit on walls and a little bit on air tightness, but just as an example of how you want to improve that enclosure. I'm not diminishing the needs for better windows, just in the limited time we have, the topics we want to cover. We'll start with walls and air tightness. And I'll just highlight that this all starts now with the 2021 ICC becomes the basis of design for the Energy Star program and for the efficient new home program by DOE. And just noticing the various elements, the ones in red are the ones that have changed. I'm actually going to highlight those for the climate zone that I suspect you're all in today. And looking at, let's say, climate zone 5, the walls, wood frame walls, 30 or 20 plus 5. And we always like to point out in the building science world, and in what world does 20 plus 5 equal 30? Well, in the effective R value world, in the thermal bridging world. And what we're seeing here is an increase in wall performance that's being highlighted. And again, many of you will be above these levels, but I just wanted to show where this 30 and 20 plus 5, what the elements are around this, why we're talking about those particular elements. And it all comes down to thermal bridging, right? That roughly 25% of our walls in wood frame construction, somebody on this call undoubtedly is doing ICF or SIP panels, and you can say we don't have that. I get that, but I'm speaking to the wood frame construction, roughly 25% of your walls made out of wood. And when we look at that, there's 30% in terms of framing, not 25, but 30. But looking at the effect of our value of that wall, right? When we take all of the insulation elements, the films, the exterior insulation, the framing, and so on, there's the effect of our value. And the code is saying, I've been there, done that. We have to get past this. I know it's not easy to change the wall thickness, but isn't there a better way of doing this? Well, of course, there's a better way. And here's an interesting idea. If we simply spent a little more time at the top left thinking about how much wood we put in a wall, actually go back to 2x4 walls and put 2 inches, typically 2 inches, R10 worth of insulation, maybe it's 2.5, depending what insulation you're using, we can actually get an improvement. Notice that number of R5, actually R6 over 14. That's about a 40% improvement in your wall at the same wall thickness. And the point we're highlighting here, and maybe I'm alluding to what we're going to talk about in 2 weeks' time, is let's rethink. If we're at the point where we're finally going to change your walls, maybe it's an opportunity to rethink that conversation and do it cost effectively, because frankly, this would have nice implications on the embodied carbon side as well, depending on the materials you chose, and I get really good performance. So in this world, a 2x4 wall with R10 gives you better performance than a standard 2x6 wall, and it gives you effectively the same performance as a 2x6 wall with R5 on the outside. Isn't that interesting? The key here is that the code is recognized, and building science has recognized for decades, that it's not the nominal insulation value that we're interested in, it's the total effective R value. And I know this has challenges, lots of yeah buts to this, and we're going to cover that in a couple weeks' time. The yeah buts of how do I put that insulation on the outside? How do I attach my clouding? What happens to my foundation width? What happens to the width of the house if the walls are getting thicker? All of those are significant and of interest, but what I want to allude to is they really help in terms of the electrification. If I tied it back to electrification, when I finally fix the walls or do better on the walls, it dramatically reduces loads in the house. And these kinds of numbers that you're seeing here, this effective R value walls of 20.26 is the level that gets you reliably to zero energy levels. It certainly meets code, gets you past Energy Star version 3.2 and gets you onto the zero energy program, or that idea of zero energy. Wouldn't meet passive house requirements, many would know, but at least it's a starting point to get us where we want to get to. Second on the list is that finding and minimizing air leakage, which has been an age-old issue of how do I find and how do I impact those? What trades are involved in that? So we've known about this for about 40 years, that air leakage is our single biggest heat loss mechanism, if you will, and therefore we have to address it. The good news is there's been lots of new technologies around this, water-resistant barriers that are used as air barriers, coated sheathings used as air barriers, insulated sheathing, XPS boards, and so on, and a technology that I'll show you in just a second in terms of AeroSeal. And this idea of how tight do we want to get? I often like to turn this conversation around, because we sometimes hear builders, architects, and others say, we don't want to make it too tight. And so I like to pose the question the other way. If you were building a brand new house today, if you were a homeowner and having a brand new house built today that was going to last for the next 100 or 200 years, exactly how many holes would you like the builder to leave in the walls or attics of that house? And of course, the answer would be none. Nobody wants unintentional leaks in our houses. We want our houses to be ventilated, but we didn't get ventilation through electrical outlets. We got ventilation by opening windows. So this idea that somehow we want air blowing through our walls, no, that nothing could be further from the truth. And if that's foreign to you, I'm sure it's not if you're a regular to this series, but if it is, then frankly, you do need to commit yourself to more training. But this idea of getting down to at the bottom two lines, that the idea of zero energy goal of 1.5 or the passive house goal of 0.6, by all means, lower is better. So keep going. But these kinds of levels we know to be really cost effective. And I'll show you the impact of those in just a second. And some would say, well, that's difficult to do. Well, now there is a technology called AeroSeal that'll do that for you. And I'm showing it just because I think as a fellow who's been doing blower door testing for 35 years, to me, this is a bit of a game changer. It means that every builder in North America can be at whatever air tightness level they want, 1.5, 0.6. And I'm not saying this is an easy out. You still have to build a good house. But in fact, you can dial down the air tightness of just about any house. And I mention that just in case people are concerned that how do I do what does the house need to be airtight to get electric? Well, you want to reduce loads as much as possible, as much as practical. And this has a very practical implication when it comes to employing new heating, all electric heating technologies, such as heat pumps. I'm just showing the animation of that sealant. It's just a sealant that's finding its way to all the holes using the blower door as the mechanism to push the sealant into building envelopes. And the key out of this short conversation that we just had was that these technologies, like better air tightness, better walls, better windows, better basements, help you lower the peak winter design loads, which reduces A, the size you might need for a heat pump, or B, the size of an electric backup you might need. To me, more importantly, in my case, the cottage that loses electricity for 6 to 8 days a year, winter days, because the building's so well insulated. In fact, I haven't had the heat on yet this year. I am going up this weekend to the cottage. I haven't had the heat on. This is north of you folks. I'm in north of Toronto, Canada. I haven't had the heat on yet. And the temperature in the house has only dropped to about 57 degrees without any heat. Now, I've turned it on today, and now I guess I'll start heating it now. But the idea here is that when you build a good enclosure, people often say, well, if the power goes out, I don't have any power, I can't run the heat pump. Well, you can't run a gas furnace either when the power isn't on. The point is that makes the house more resilient. So it adds to the durability and resiliency of a house. It also reduces peak summer cooling loads and helps you or encourage you to manage the intermittent nature of solar gains. It turns out that we don't actually do that much cooling. Not a lot of energy is spent on cooling houses. The problem with cooling is windows. Everybody wants more and bigger windows in their houses, and that creates a challenge with respect to the intermittent nature of those cooling loads, the instantaneous load of how big I need for tonnage. And so when you've managed the heat loss and managed the peak summer gains, that really facilitates the balancing out of heat pump sizing. And I'll highlight that in just a little bit here is where we're headed. So minimizing air leakage, improving effective R values, and putting in high performance windows, and ultimately full foundation insulation, including under the slab, really cost effective from a load management perspective, from a resiliency measure as well, is important. And so that's a short conversation. That was element number one of the path forward to all electric, is get your enclosure optimized below 2021 levels, if you will, better than 2021 levels, in around that zero energy range. You'll find heat pumps become more applicable, if you will. And hopefully you all have a sense of heat pumps are transferring heat. They're not creating new energy. They're simply taking free heat that's already in the air in Connecticut, using that heat through the magic of refrigeration to heat your home. And basically you have this pump, we call it pumping or compressing the heat. It's maybe a simple terminology. It's not technically how it works, but we can chat about it. But it's transferring, pumping a refrigerant between in and out. And for every kilowatt it takes to run that pump, you get 3 kilowatts of energy delivered to the space. The most efficient gas furnace you can buy is around 98%. Electric space heating, old baseboards are 100%. This is 300% efficient. So that's why it's really interesting, because now I don't need as much electricity. People say, well, electricity might be more expensive. Yes, but it's 3 times more efficient to run it than it is to run a fossil fuel generator, if you will. So keeping that in mind. And I will highlight, just mainly so that this is in the slide deck when you get a copy of it, or you rewatch this. I don't know if we're doing the slide deck, but you are going to be allowed to rewatch this. But understanding that we're relying on this magic of refrigeration, of air blown across, down the bottom left across the evaporator on the outside, that's absorbing heat from the outside air. Then the pump works to increase that refrigerant's temperature and pressure and dumps it across the condenser that releases that heat. So we evaporate and absorb energy on the left, and we condense and release energy on the right. And it turns out, a simple analogy is it's making Connecticut colder while it's making your house warmer. It's a technology that's simply transferring energy from one location to another. And the good news is, even in the last 10 years, 15 years, there's been a real explosion, both in terms of the number of options and the performance of options. So these terms will undoubtedly be familiar, but air source heat pumps, but the multi-terminal multi-splits and mini splits, so that you could have different, not necessarily needing ductwork, use refrigerant and different types of terminal units to heat your house, or indeed ground and water source heat pumps. Now variable speed cold climate heat pumps. Some would say, I still want to keep some of the fossil fuels. Okay, we could do hybrid heat pumps and use that as a backup of heat. And we're seeing there on the left, air source ducted. I just wanted to highlight ground source again. On the top right, air to water heat pumps starting to come across. So specifically houses where you want to do, say, in-floor heating or radiator-based heating, hydronic-based heating, we're starting to see products that can take heat from the air outside and bring it into the house. This has a secondary advantage. In these cases, the lines that are running to the house are not refrigerant-based. These are hot water and chilled water, which takes away some of the complexity of refrigeration, right? We don't need a refrigeration mechanic. All of the refrigeration is done inside the box outside. Think of it as a freezer. No issues from a connection perspective. I'm not managing refrigerant. I'm managing hot water. All of that's done inside the box. And the bottom there, the heat pump water heater is another, another technology I want to get to. This little animation just showing that process of how things are working. In the tubes between in and out are the refrigerant that's either in liquid form or vapor form. On the left-hand side, that evaporator that's evaporating the liquid refrigerant into a gas. And as it evaporates, it's pulling in heat, taking heat from the air outside, dumping air that's cooler. On the right-hand side, releasing that energy in the condenser and turning it back into a liquid. So a gas and a liquid refrigerant moving back and forth between the inside and outside. I thought you might be interested in that. In terms of efficiency, because you will hear different terms, there's two terms. The one I like using is COP, coefficient of performance, which is a ratio, a unit in versus unit out in terms of kilowatts. As I mentioned, a typical heat pump is has a COP of 3 to 4, 3 to 400% efficient. The industry chooses, HRI for the most part, chooses to use HSPF, heating season performance factor, which gives an account there in the bottom left for the total heating output, which they happen to put in BTUs, compared to the total electricity consumed. We're an industry that is always been fixated on BTUs, 70,000 BTU furnace, whatever. This is trying to mimic that and saying, there you see the formula, heating output in BTUs versus electrical input in watt hours, if you will. And so an HSPF of 3, sorry, an HSPF COP of 3 would have an HSPF of about 9.5. In other words, we're taking kilowatts and turning them into BTU. So just a little example, two different metrics that you're going to have to get familiar with. Sometimes that can be confusing, but hopefully you're feeling comfortable with those two different metrics. The biggest piece associated with heat pumps is to get the size right, both for cost and comfort. It is absolutely true that if we had tried and did try to do heat pumps decades ago, our heat losses in a house were so large that you couldn't practically put a heat pump in. There just weren't heat pumps large enough. Now that you are building houses that are more efficient, even from a code perspective, you went from a HERS index of 100 down to a HERS index of, say, 50. You've cut heat flow in half. You've cut almost always the design heat flow for the house in half, and therefore heat pumps become more viable. Important out of that, though, is to get credit for that, to do a proper heat loss, heat gain. Hopefully, new construction builders are doing this, but even if some of you are doing replacement work, renovation work, you should be doing these calculations. And there is an association, the ANSI Association and ACA, Air Conditioning Contractors of America, that provide the software that allows you to do proper heating and cooling. And I'll highlight a couple of those issues. There is the output from, you don't need to read the numbers. It's just showing you the output. It gives you a sense with the graphs, with the pie charts, where the energy going. On the left-hand side, what we end up with is if we don't size correctly, we get short cycling, poor humidity control. And from this conversation, extra costs from equipment and ductwork. If you want to get to all electric, you're enabled to do all electric if you can get the heat pump sizing, A, smaller, and B, correctly sized. And third, C, balanced. You kind of like the heating and cooling loads to be closer together, if you will, is what we'd like to get to. And in terms of heat loss, heat gain factors, on the heat loss side, you'll see it includes the envelope, the surface area, how cold is it outside. I've highlighted air leakage and ventilation because they are the biggest portion. The instantaneous load on the coldest day of winter is the single biggest component, is always the air leakage. And so we keep that in mind. On the heat gain side, the biggest component is always the windows. Windows account for between 50 and 60% of air conditioning loads in Connecticut. The size of the heat pump, size of the air conditioner that you need, fully half of that is associated with the glass and which way it's facing. So managing those two loads really helps from a heat pump sizing and comfort perspective. So keep that in mind. And I'll just reiterate again, 40 to 60% of cooling loads associated with windows, 30 to 40% of heating loads, design day heating loads associated with air leakage. And when we get those two right, we're in good shape. Here's a little example, maybe a slide you want to concentrate on a bit or take a picture of. This is a notional 2,275 square foot house in your climate zone 5, and it's showing if you'd built that house, when that house was built to the 1990 code, that was 70,000 BTUs and 20 kilowatts. That would be the equivalent of 20 kilowatts of electric heat. The air conditioning load would have been, well, we weren't air conditioning much back in the 90s, but 3 tons, 36,000 BTUs. Notice what happens as you get to even the 2012 code, or more importantly, the zero energy ready standard. We've cut that by basically 2/3 those loads. And more importantly, look how close together now the heating and cooling loads are. They're only 10,000 BTUs, less than a ton difference between the two. That makes it easier to size a heat pump because you don't need it. There was no such thing as a 70,000 BTU heat pump. That would have been a 6-ton heat pump. It's residential level. It's really not even available. So, but down on the right-hand side, to the right-hand side, you're seeing roughly 1.5 to 2.5 tons is all you would need for that house. So down at the bottom, the key is in addition to things like smaller ductwork, there's some cost savings there. The optimized enclosures help balance those heat pump loads, and they minimize the service panel loads. Because if you were trying to do all electric back in 1990, boy, how big a breaker do you need for 20 kilowatts of electric heat? So thinking about how these optimized enclosures help us get to heat pumps, better heat pumps is where we'd like to get to. The next piece, though, is to understand, how do I choose that heat pump? So first it's conduct that thorough heat loss, heat gain, and then check manufacturer specifications. And you go, how do I know it's going to work in Connecticut? Good news is right there in the Northeast, there's the NEAT program, the Cold Climate Air Source Heat Pump List. They've brokered and gotten this registry that's showing you the capacity at different temperatures. And that's the key. You would look at, and the graph's pretty complicated, but it's pretty straightforward. You try to look at, notice that green line that's going from bottom right up to the top left, if you will. That's that dotted green line. That's the heat loss of the house. It gets colder outside. I need more and more energy, more and more heat on the left-hand axis. And I try to find the sweet spot of, well, how cold does it get here? how far will that heat pump run? That's the key to this. And the big difference is furnaces, the high efficiency furnace, regardless of what the temperature is outside, that's the gray line. It did what it needed to do. It gave you that 48,000 BTUs. The standard old heat pump 20 years ago, that's the one in gold. Notice how its performance drops off. Its capacity, as it gets colder outside, its capacity drops off. And in fact, at about 10, 12 Fahrenheit, they cut off altogether. You had no energy whatsoever, and you needed emergency or supplemental heat to make up that difference. The change in today's world is we now have these high performance cold climate heat pumps that continue to operate. They don't shut off. They keep running all the way down to -20, -30. They may not be able to keep up the entire capacity. Notice where it intersects the heat loss line at roughly -10. So if you're going to be colder than -10, you might need a little bit of supplemental heat, but you don't need the 100%. And that's the big difference in today's world. And it really allows you to be confident in going to all electric because you now have rated appliances right there in the Northeast. Rated appliances do indeed work, continue to operate at even really cold temperatures. So that's pretty critical. Notice the difference here between a standard heat pump, that's X24 there on the left, and how it shows its heating capacity at 47 Fahrenheit and how it's dropped pretty significantly, even down at 17. And they don't list at all what it'll do at 5 because, frankly, it's turned off. It's not going to run at 5 degrees Fahrenheit versus the two cold climate heat pumps that are able to keep running, maintain their capacity all the way down to 5 Fahrenheit, keep running past that. They're not cutting off at 5, but keep running past that. And therefore, only small amounts of backup heat are needed. Sometimes you can do it entirely with the heat pump. Sometimes you need a little bit of backup heat. So what do you do for backup? Well, there's the heat pump on the left. There's a coil on top of it. It could be electric, it could be gas, it could be hot water. So if you want to be all electric, a little electric heater on top, or if you still have some fossil fuels in your house, say heating your hot water, you could use hot water for this. What's really nice is the heat pump keeps working even when it's really cold, and you're just topping up the temperature, if you will, as it gets colder and colder outside. That's the key to this conversation. There's a lot of people opting for hybrid, so they'll keep the gas furnace there at the bottom left, and then they'll put the heat pump coil on top of that. The downside to that is you're not really electrifying, number one. And number two, the heat pump can't run when the gas furnace is on. You can't put warm air over top of the heat pump. So you got to kind of make a choice of which one. And it doesn't allow you to optimize the use of the heat pump, and nor do you qualify for your incentives that Keegan was talking about earlier. So keep that in mind as we go through this. Next on our list, I just want to mention the importance of, because people are worried about the reliability, the importance of verifying performance. And in today's world, we have technologies and standards that allow us to verify the performance. This is actually at our facility in Denver, where we're demonstrating the technology of what's called ACA 310, which is the verification procedure, where you're adjusting speeds and dampers, you're taking 4 or 5 measurements, and you're verifying that the system is actually working to the manufacturer's specifications. It is a 5-step process where you do a design review, you understand duct leakage, you measure the blower fan, both its airflow and its watt draw, and you take a refrigerant charge, and it gives you a test performance for that system. There's the rating. For example, this system is working at 94% of its rated capacity. Some homeowners are going to say, I want 100%. Fair enough. Let's tweak it. But wouldn't it be nice to know that you're able to achieve the day you move in, the day the system is commissioned, working correctly? And I would put it on your list of things to do. If you're going to go all electric and you're going to be at heat pumps, and you are, then you would say, I want to add this. I want to make sure my mechanical contractor or my certified energy rater, your energy rater, is able to do this testing to verify for your clients that the system is working correctly. So keep that in mind. I do want to remind you that in addition to houses getting better, more efficient, which allows heat pumps themselves have gotten better. We now have this very variable compressor and refrigerant flow. We now have electronically commutated fan motors. both inside on the inside and the outside unit, which allows systems to run more accurately and higher statics, more precise thermostatic valves, improved coil design, smarter controls. Most importantly to me, cold climate testing. That NEAT testing, to my mind, is the game changer that shows these pieces of equipment do indeed work down to those low levels. So if you or your contractor are still nervous about heat pumps and whether they will work in your climate, I would encourage you to commit to researching, embrace the new technologies, talk to the manufacturers, go look at the NEAT data. You'll find literally thousands of combinations of heat pump that can work in your climate zone reliably. So keep that in mind. And I'll just mention again, here's the beauty of heat pumps. Notice the standard heat pump in gray that pretty much cuts off at around 10 Fahrenheit. The one in red continues to work all the way down to minus 25. And maybe it doesn't have its entire capacity, but at least keeps its capacity. Here's the definition of cold climate heat pump. Maintains its capacity nominally down to 5 Fahrenheit, maintains a COP, remember, COPs, watts in versus watts out of at least 1.75. Even at 5 Fahrenheit, it's 175% efficient. Can I say that again? At 5 degrees Fahrenheit, cold climate heat pumps are still working. For every dollar of electricity you buy, you still get $1.75 worth of heat into the house. And most keep producing heat down to as low as minus 25. Then you simply ask the manufacturer, do you have a cutoff temperature? What is it? Do I need backup heat? And you can always manage it with a little bit of backup heat. So keep that in mind. Next, I did mention we'll go to water heaters quickly. We're doing pretty well on time. Might be a few minutes over, but we still have lots of time for questions. Noticing here, we have heat pump water heaters, which are doing basically the same thing that the air source heat pumps are doing. It's taking heat from the air, in this case, from your house or garage, taking heat from the air and turning it into hot water. And similarly, they have amazing COPs. The most efficient water heater you can buy these days, say a tankless water heater is 95, 96%. Heat pump water heaters are 300 to 400%, similar to houses. And you're going to say, well, that certainly makes sense in summer because I'm using the waste heat from my house. It's actually cooling my house while it's heating the hot water. You would say, does that work in heating mode? What happens? Well, if you're heating your house with a heat pump at 300% efficient and you're heating the hot water at 300% efficient, yes, you are cannibalizing the heat from your house, but it is at the same efficiency. So it basically is working at a factor of 1 in the winter time. What we found is this didn't make sense or doesn't make sense in older houses that need way more heating than they do cooling. In low load houses, such as passive house, you spend more time air conditioning than you used to. That is, the spring and the fall, you start air conditioning sooner than you would in an older house. And so heat pump water heaters do make sense in what we call low load houses. They also have electric backup, they're connected, all of those good things. We would say they're particularly useful in zero energy, in passive house, and certainly houses that have solar panels on them. So it's pretty useful. There is a specific requirement in the Energy Star Next Gen program. They have to be Energy Star certified. They too need to be connected, which is actually pretty interesting. Water heaters are a really good storage mechanism. We don't necessarily need the water heater coming on all the time. We could control the water heater and only have it come on when we would say is most efficient or most effective to turn on. So keep that in mind. There are specific requirements for size of heat pump water heaters, Energy Star houses, and Energy Star Next Gen houses. These two provide a good guidepost of, how big do I need? And it's pretty similar to what you would need in a standard tank water heater, but just a little sense of that. There are some considerations. What do you do with that cooled air? I need a certain size room. If you have a basement, it's never an issue. But if it's a slab on grade or a small unit, multi-unit, you might have to find a way somewhere to dump that cold air. I don't normally recommend dumping it to the outside, normally into a floor joist system, something like that. And we would say as long as it's in an area bigger than 1,000 cubic feet, not square feet, 1,000 cubic feet, and you could vent or discharge to another area of the house, You could just decide to use electric heat only in the wintertime, so that's a good thing to do. They do have slightly higher sound levels. The good news is there's a rating on them at 55 decibels that they're all meeting. I have both second generation and fourth generation in different places one in my house, one in the cottage. And I would say the fourth generation is infinitely quieter than the second generation. So you're seeing quieter and quieter equipment. And if you choose under 55 dBA, you'll find it makes a lot of sense. Or choose water heat locations carefully, not near bedrooms. So we'll just do that one. Our last little piece on this was electric cooking. I wanted to highlight this because it sometimes is the toughest one to get across to consumers. So keep this one in mind. Some would say, in fact, I've done the test, hot water heats faster on a conduction oven than it does on a gas range. How do I know that? My neighbor and I have a contest that goes on, so I can heat hot water faster than he can. So I thought that was interesting. But here's where this is coming from. It has to do with air quality. I want you to notice first down at the bottom, the American Medical Association, the American Lung Association, and the American Public Health Association have all agreed to put their names on this communique from EPA to say that cooking itself has unhealthy particulates. As good as it might smell, it's not particularly good for us. Particulate matter smaller than 2.5 microns. Cooking with gas also emits pollutants, NO2 and CO, at elevated and sometimes hazardous levels. And NO2 specifically is associated with asthma and respiratory issues. Although vented range hoods can remove a significant portion, many people don't use those range hoods, and gas piping can also emit methane. So we're not saying that gas cooking is unhealthy. What we're saying is if you want the healthiest possible layer for you and your family, you would not use natural gas and you would properly vent your range hood every time you cook. From this day forward, when you're cooking, even if it's not with natural gas, vent your range hood. That's an air quality issue. So I'm just highlighting this as perhaps another benefit of an all electric house is you are indeed clearly, I'm going to say clearly, proof here that you are offering a healthier house. So keep that in mind. Now, I want to finish up with, okay, we want to go all electric. Is that okay? Do we have enough space in the grid? And it's really clear. 40 years ago, 30 years ago, we didn't. Now we would say we do. We have elements to manage this. And so we want to talk briefly about things like the peak curves that are associated with electrical use. What about the peak loads associated with atypical loads like EVs and electric ranges? What size panel do we need? And will we get recognition from the stakeholders? And you have electrical authorities right here on this call that are promoting this concept. And they're saying to you, we got you. We can do this. We can make this happen for you. So thinking about right sizing, there's the Falcon curve, and I'll just highlight it just there on the left. Notice it's January, it's an annual, January to February, the Falcon being the wings of the Falcon, big peaks in January, December, January, smaller peaks in the summer. What we'd like to do, of course, is flatten out that curve, and that's what the utilities are looking for, ways to flatten out that curve. So that's their challenge, if you will. And in fact, there is a technique or a strategy called power efficient design. So looking at the important impact of the individual loads in houses, and could we find a strategy before we upgrade a panel size, whether it's in newer and existing houses, to reduce the need to increase the panel size? Because after all, increasing the panel size could be expensive, $1,000 to $5,000 for a homeowner to do. And what if the line to the house wasn't adequate? So there's an impact. And what if the transformer on the street wasn't adequate? So huge interest in avoiding this infrastructure cost using power efficient design. So minimizing the energy consumption, increasing cost savings, lowering greenhouse gas emissions, all of these become benefits of power efficiency design. What I want to show you, and reducing the strains on the grid, I want to show you what we mean by power efficient design. And first and foremost, notice on the left is optimize load calculations. Oh, do the proper sizing. Second, in the middle, save power through energy efficiency. That's what you and I were chatting about. Build a more energy efficient house, use heat pumps that use less energy and at less peak load. Three, once you've done those two things, could you monitor and control what we would call peak shaving or load shifting? And lastly, could we use energy storage? These are more or less in order of magnitude or in terms of complexity, sorry, what's simplest to do first. So on the start with the left, get that done right and work your way to the right and see where we need to end up being. What I wanted to highlight to you is just a rethink of what I showed you before. A house in 1990, if you had to heat that house with electric, that's 20 kilowatts. That's 85 amps just to heat the house versus the zero energy ready heat pump, even an electric backup, is still only 25 amps, which is basically the same as an air conditioner. So if you already have an air conditioner in a house, already planned for it, the heat pump in a low load house, a high performance house, doesn't really add anything to the grid sizing. But that's really what we're trying to do, is optimize those enclosures to help balance the heat pump loads and minimize service panel loads as well. So a little example is just showing, if you didn't upgrade the house, how many solar panels would you need? We want to be away from that. So in terms of this conversation, I'll go back one. Not only does this make it easier for the grid, but what if I wanted to electrify my house? Once I've done a zero energy house, I don't need nearly as many solar panels to energize that house. So I just want to keep that in mind. And if we look at, say, in an individual house, the peak daily, day hourly profile in the winter, what's happening throughout the day, how could I shape that load? How could I shift that load? And there are technologies available for that. First and foremost, though, we'd want to check our electrical capacities. We'd want to look at the continuous loads, the big loads, the electric space heating, the air conditioning, domestic hot water. Basically, most codes, I won't speak to Connecticut codes, but most codes would say take continuous loads that are more than 1,500 watts for more than 1 hour in any 2 hour period. You would understand water heating, kitchen range probably falls in that category. And typically, historically, you had designed your panel to meet 80% of that load couldn't exceed 80%. So for example, in a 100 amp panel, you couldn't be using with those continuous loads more than 80 amps on a 200 amp panel of 160. So you go, what can I do with 80 amps? Well, I certainly can't put electric baseboard heating in an old house on 80 amps. But if we look at a typical house, domestic range, electric kitchen, electric clothes dryer, if we look at that total amount used, 11.5 kilowatts, so what do we have remaining? We have the ability for 7.7 kilowatt hours. And if a 3-ton heat pump at 1.75 COP uses 6 kilowatts on that very cold day, we can do that. We have enough room in that 100 amp panel because I have available to me about 19 kilowatts. So if careful, and if we have, careful is the wrong word, if we are accurate in our sizing and we're accurate in our understanding of how a low load house works, then in fact, we may not need to upgrade the panel. In addition to that, there are now low recognition of load shifting and shaping. The connected water heater, remember I said Energy Star requirements is for connected water heaters? The theory is, the principle here is that the water heater doesn't need to necessarily come on every time you take a shower. There's enough volume of water to last for 2 or 3 showers. Let's hold off on that. Let's connect it. Let's tell it don't come on until the rest of the house is no longer at peak. There's a new technology coming to North America out of Europe where they don't use a storage tank of hot water. They use a phase change storage material. So they heat up this phase change material and it's able to store heat or thermal, if you will, and the cold water passes through it. Inside that box or those boxes are not water. It's actually a phase change salt with pipes running through it that heats that hot water. So you're going to see those load shifting elements. On the right-hand side, a profusion of panels now coming. This is a particular manufacturer, Span, who's able to manage loads and is able to say dryer and air conditioner shouldn't run at the same time. EV and dryer don't need to be on at the same time. So on a breaker by breaker basis, can rationalize out. And we're finding large builders are able to use this in their communities to avoid oversizing transformers, and utilities are working closely with them to say, if we have a constraint in a particular neighborhood, we can use these kinds of strategies to reduce the panel sizes and therefore the transformer sizes. Indeed, a couple of examples of using solar panels and a bidirectional charger and a home battery to flatten out the peaks in this house and show that it can stay within 100 amps. A grid integrated entire development, Mandalay Homes out west, that's understanding that the grid is helping manage their loads, and the homeowners have selectively said, I won't use particular specific appliances at peak times. In fact, they have controls that allow them to do that. And by the way, those controls have been on houses for decades. This has been done over the years, many, many times. Similarly, here's Soleil Lofts, where it's utility connected, independent energy island, virtual power plant, where they are monitoring and turning things off and on based on what's happening in the entire community to minimize loads. And there's the concept that each individual person, Peter and Paul and Martha and Magda, they're all connected with little local microgrids, everybody sharing that power and sharing that energy with this smart grid storage. So pretty useful. So as I finish up my last 2 slides or so, I'm going to suggest to you this compelling message of electrifications. 1, 0 emissions at the house. 1 meter as opposed to 2 in terms of a second fuel. I've suggested to you that they could be healthier and safer. You may decide that that's not true for you. I mentioned to you, I believe it's future proofing and flexibility, because with battery storage and with load shifting, that in fact it could be very useful in a future sense. I like the idea that this simplifies your life, less moving parts, if you will, less moving fuels, if you will, and a built-in durability and resiliency. And I say that because, not because the heat pumps are necessarily more durable, but the same things that you do to make heat pumps more viable, that is, make houses more efficient and so on, also makes the house more durable and more resilient against power outages, against climate change, against weather events. So that's my messaging to you, if you will. I will just ask if there's any questions. Don't know if we needed follow-up slides. Also stop sharing, I think, unless we need to. I will just open it up to questions. I guess a few minutes over, but not so bad.
Awesome,
Keegan or
Gord.
Kate,
Thank you.
anything there in the chat that we want to address?
There was a comment, I think somebody, yeah, there was a comment in the chat that from Rainer that listed some additional strategies that work well together and worked well for us,
Great.
including combined radiant heating with GSHP, cooling with chilled water, and the house being backed up with lithium batteries, which also power the house during the day and charge at night when the grid is abundant/cheap, and adding bidirectional charging for electric cars. So I guess if you wanted to comment on any of those, I also will look to see if anybody has a hand raised.
Sure.
Also, yeah.
I really love, sorry, thank you for that. I'll just comment on what he said, because that's very similar. I think the flexibility that you get with hot water is pretty useful. What we've lacked up till now is a way to heat hot water with electricity other than heat pump water heaters. Ground source certainly can do it, and that's so I love that. And I think the new air to water concept, so that I could do some radiant heat in a floor and charge up a floor at night, for example, off grid. So I think that has huge benefits. Even that phase change material, you just use straight electric off of that, but or a heat pump, air to water heat pump. So I see huge benefit in using water-based systems, hydronic, as long as we can sort out the air to water heat pumps or the groundwater, water to water heat pumps. You're on mute, sorry, Kate.
Yes, thank you. And I think Rainer does have had his hand raised, but now it's not, so I assume that questions or that comment is answered and all set. There's another question in the chat, but just oh, okay. I'll allow Rainer to talk now. Should be able to
Hello,
talk.
can you hear me?
Yep.
Yes.
Yes. Hi. Very good talk. Thank you very much.
You-
I'm an architect, so I have a house built 8, 9 years ago, all electric, with a ground source heat pump with radiant floor heating. And I just wanted to maybe add to your talk the importance of the delivery method of the heat into the house and the cooling, and how beautifully radiant floor heating works with a ground source heat pump or any other heat pump, which can deliver water to only a certain temperature. And radiant floor heating, because the heat exchange is so large, basically your entire floor doesn't need a lot of water temperature beyond the air temperature, maybe only 90 degrees or 100 Fahrenheit. And the heat pumps are great at producing that kind of temperature. As you mentioned, you don't need a hot flame that can do several thousands of degrees for that. And
Indeed.
I also wanted to add the importance for the utility side, how good it is that they offer net metering, because if you have solar power, you often don't need it when it's there. During the day, you might not be home and the sun shines, and you can use the grid as your battery basically for the house. You give it back when you don't need it, and there's plenty of other people who need it during the day, and you get it back at night when the heating needs to come on, and when it's cheap.
Thank you. Keegan or Kate, can you comment on that? The utilities in your area, are they allowing net metering?
Yes.
Right.
Yes.
Keegan's nodding his head as well. Thank you for that. I totally agree with you. When we use hot water, like gas-fired boilers, to a large extent, when you're doing in-floor, you're dampening down the temperature because you can't put 140-degree water into the floor. So I agree, Rainer, entirely that there is a nice synergy between air-to-water heat pumps or water-to-water ground source heat pumps to radiant heat. We have had some issues. It becomes a bit of a control challenge when that floor gets heated up in certain climate zones. In the spring, for example, it heats up too much during the day and it's hard to turn it down. So we can sometimes get some overheating, but that typically can be overcome with proper controls of temperatures of both the water and the floor. But so I love that. I notice here a question on with upcoming new building codes in Connecticut to be adopted, how does that next gen efficiency standards compare to that? Well, remember the next gen is based on a 2021 code. So you're pretty much there. The 2021 code plus Energy Star requirements version 3.2. And Energy Star 3.2 is deemed to be 10 to 15% better than 2021. So in other words, you're 10% away. Your code at 2021 is, let's say, 10 to 15% shy of Energy Star. And you go, well, that's pretty easy to make up. That's the point. You are at the point now where it doesn't take much to get to the next level. The synergies of the last, I'll say it this way, the synergies of the last 30 years of energy efficiency improvements, windows, air tightness, walls, you take all of that, and absolutely in 1990, I wouldn't have put a heat pump in a house in Connecticut. But now in 2025, why, of course you should put a heat pump in a house. In fact, I say on every call I have these days, never buy an air conditioner again. It never makes sense. You talk to all the major manufacturers, Carrier, Lennox, Trane, they'll all tell you they won't be making air conditioners 10, 15 years from now. They'll only be making heat pumps. Even if you don't use the heat pump 100% of the time right now, it's still your air conditioner. You need that box anyway. So that's why it makes sense. So thank you for that. And then I see Robinson's asking, he's part of a housing co-op looking to build a series of small houses. Are there particular considerations for small houses that differ from standard? Well, I actually can address this. You may want to look up Doug Terry Homes in a place called St. Thomas, Ontario, who's doing tiny houses, net zero levels. He's going through this right now. Here is what his challenges, I would say, would be. First and foremost, the water heater, the heat pump water heater. What do I do with the cold air? It's a problem. Now he's talking 500 square foot, 250 to 500 square foot dwellings. So it's pretty tiny. And he's finding it a challenge. What do I do with the heat pump? He's been sorting out the heat pumps. It's hard to find ducted heat pumps, that is traditional ducted heat pumps that are small enough for those small houses. But there are mini ducted systems from the folks like Mitsubishi, Fujitsu, Daikin, all have cassette type units that are mounted in ceilings that are low enough loads. Because in those houses, you might be as low as, well, under a ton in many cases, depending how efficient your houses are. So there are technologies available. So that's useful to know. So thanks for that question. And I would encourage you to keep looking, lots online on this, and we could think about another session, I guess. There was another comment that says ICC 2024, and I agree. In fact, 2024 is easier to do than 2021. All builders have told us the sooner we can switch from 2021 to 2024, the better. It is slightly more efficient. It's not significantly more efficient than 2021, but it's more flexible. It has more flexible elements to it in terms of using different components, air tightness, and so on. So that's pretty useful. Do you mind me reading the questions, Keegan or Kate, or would you rather?
Yeah,
You okay
no,
with that?
Gord, yeah, keep it rolling.
The next question is, at what point does the extra ground source heat pump installation cost payback versus cold climate air source? This is a really good question that if this is being recorded, I'll get all kinds of comments on. And let's be really clear. I am agnostic. I think the world of ground source heat pumps, and I think the world of air source heat pumps. I think there are considerations outside of cost. I'll start with this one. Ground source heat pumps, you don't have to hide or listen to outdoor units. That's a value. Two, your dollars are put under the ground. Some would say that's more reliable in the long term. Some would say, what if something happens to the loop? I think that's unlikely. So I think that technology maybe has some durability elements to it. I think there is reason to believe that ground source is perhaps better suited to larger projects, larger, and maybe even district heating. So you're doing 4 or 5 houses off one system. The loads are pretty small in certainly in passive house and in zero energy ready houses. It's tough to even find a ground source heat pump small enough. And air source on the other side, air source heat pumps have come a long way, and cold climate air source heat pumps have been a real game changer. That said, they are significantly more expensive than other heat pumps. They're still less expensive than ground source in most cases, but they're not as the danger we have, frankly, in my opinion, is people opt out of cold climate or ground source and I'll just put in a regular heat pump. I'll put in backup heat. That to me is a cop out. I don't think that works very well. So I think you need to make the decision in Connecticut for folks who are on this call, cold climate and ground source. That said, I wouldn't necessarily, I'm not advocating that you have to size the cold climate heat pump for exactly the load. I have no problem with a little bit of backup. There's a little 4 kilowatts or 3 kilowatts, a bit of a toaster in there to help manage discharge temperatures, whether it's ground source or not. It always makes sense to undersize ever so slightly, whether it's ground source or air source. So you're not paying for extra tonnage. You're only going to use 50 hours a year. Let me say that again. When you do a design heat loss, you don't have to design it for the last 50 hours. That can be done easily with a little top of 2-3 kilowatts of electric, and that makes them more cost effective. So I don't know if that's helping, other than I would say it's more than just cost. There's other practical considerations of the outdoor unit, the indoor, have I got the ground? I'm going to add another one. The ground source heat pumps. Do the geology or the geotechnical correctly. We see ground source that's put in without the right geotechnical analysis done, and people aren't getting the COPs they thought they were because of the conductivity of the soils wasn't correct for the loop size they put in. I'll put it the other way. The loop size wasn't correct for the ground soil. So for the ground. There you go. And then there was a question about wood fires for supplemental heating. Most historically, the most efficient houses I've ever worked in almost inevitably want a wood fireplace as backup or for the aesthetics. And the question is, can you do it? And the answer is yes, you absolutely can do it. Okay, the house is airtight. The appliance needs air to burn. Okay, let's choose an appliance that doesn't need as much air. That's EPA rated. So always should be an EPA rated wood stove or wood fireplace insert. We're not talking about an open hearth where you can toast marshmallows anytime you want. So an EPA rated box uses far less air. Two, it needs typically makeup air. So you have a duct that opens when the wood fireplace is on and an exhaust appliance is on. The technology is there to do this safely. Air quality is an interesting one because certainly the all of the particulates and so associated with wood and wood storage, the cleanest of wood burning houses wouldn't be as clean as an all electric house. But so you just that you have to live with a little bit, the cleanliness of and where am I storing the wood and what sort of bugs are there. And then it's a really good choice of a wood stove, EPA rated airtight wood stove slash wood burning appliance with makeup air. And Rainer's basically saying the same thing, that closed combustion, yes. They are not technically, even with fresh air ducts into them, they are not considered direct vent sealed combustion. There's far less chance of spillage, but there's no wood burning appliance that's qualified the same way that a high efficiency gas furnace would be for zero combustion spillage. So keep that in mind. So it's a little bit of a risk. Homeowners need to know that it's a manual event. They have to manage it. But I do hundreds of houses a year as an energy rater. Hundreds is an exaggeration. Over the years, done hundreds that are incredibly tight houses with really beautiful wood burning appliances that work really well in those tight houses.
Awesome. Yeah, thank you for
Yeah,
the thorough
I
answer.
know we just have a couple minutes left, and it looks like that's all the questions for now. So I did just want to plug again next Friday, excuse me, 2 Fridays from now, December 5th, we'll have the second part of this series featuring Gord, high performance enclosures, exterior insulation that pays off, exploring how continuous exterior insulation can help meet evolving energy standards while improving overall performance. And Kate, I know you had a few events in Connecticut, Build Green CT, Connecticut House Faust that you wanted to touch on. So,
Yes, yeah. And so, yeah, thank you, Keegan. And thank you, Gord, for this presentation. Learned a lot. And also I was using I think it's EPA approved fireplace last night. So, and I was able to, manually do that and I remembered. Um, but yeah, I did want to say, I just put the link in the chat for the Gord's next webinar. And then also we have our birthday benefit coming up on December 4th, which is a great way to kind of get to know our organization because we are a nonprofit dedicated to increasing awareness about building or higher performance like this and also more sustainable construction and projects. So if you're not familiar with our organization yet, this is a great chance to get familiar. We also, for members, we do have an opportunity for folks to share a project that they're working on. So that'll be a cool way to kind of break the ice and get familiar with projects in the area. The link to register is there. And then we also have our Green Building Impact Awards coming up next year. So 2026. Registrations are open now for anyone that has a project that they're working on that they think might be an industry leader in one way or another, or it's just really cool and has a lot of sustainability features. We're looking for that. So all projects are going to be included in our project showcase during the event. So, if you want to get your project out there and seen, this is a great way to do it as well. Again, link to register is in the chat. So yeah, I hope to see all you attendees at the birthday benefit and also applying for our Green Building Awards. Early bird registration ends today, but it only takes 3 minutes to register. So get to it. And that's it.
Very
Yeah.
cool.
Thank
Very cool.
you.
Yeah,
Thanks, everybody.
thanks, Kate. Gordon, thanks so much for joining us and sharing your expertise. We'll see you in 2 weeks. And thanks again to the sponsors of Energize Connecticut for hosting and putting on today's training and all the trainings that are part of this series.
Absolutely.
Thanks, gang.
All right. See everyone in 2 weeks. Thanks, Kate. Thanks, Gordon.
See you in 2 weeks. Bye.